Hello everyone and welcome to the next video in the series. This is a technical skills video on the topic of the structure of scientific notation. What I would like to do in this video is talk about why is it that we need scientific notation, and then I will point to some of the features of this notation that are quite attractive when we work with certain kinds of numbers. As far as the use of scientific notation goes, scientific notation makes it easier to work with, and by that I mean compare, add, subtract, multiply, and so on, numerical values that are either very large with a string of zeros on the right end of them, or very small with a string of zeros on the left end of them. So as an example of that, I have one example of each. For number of entities in 1 mole of an entity, we have this number. There are so many things, so many entities in 1 mole of an entity. So a mole of electrons would have so many electrons. This is a huge number. And as you notice, it's a very large number with a few non-zero digits, and then followed by a string of zeros on the right hand. As an example of a small number with left end zeros, we have the mass of an electron. This is an extremely small number, as you notice. There are many zeros on the fractional side before we get to non-zero digits. And of course, the reason is because we are using grams as the unit of mass to measure the mass of something that's extremely tiny, that of an electron. And then, of course, we expect that the value will be very small. But we do have the features that we talked about here. This is a very small number with a string of left end zeros. Now, these numbers you don't encounter them all the time. It's depending on the field of activity that you're in. You may see them less frequently or more frequently, but in any case, when they come up, it does pay off to know scientific notation, because as they stand, this notation is extremely annoying to work with. Think about trying to find the mass of 1 mole of electrons. This is the mass of 1 electron, and there are this many electrons in 1 mole of electrons. And therefore, to find the mass of 1 mole of electrons, or the molar mass of electrons, if you like, we would have to multiply these two numbers. Now think the algorithm that I told you about in an earlier video on multiplying decimals. We would have to start by dropping the decimal point, and then we'll end up with this whole thing, as well as 9,109, and then we multiply the numbers without their decimal points. We can speed this up a bit by dropping the zeros here and multiplying only 602 by 9,109, and then add on the zeros. It's still a lot of work if you think about it, and we're not done yet. I would have to count all of these zeros so that later when I add them on, I know how many I should add, and I have to be careful not to miss one or add an extra one, because if you miss one or add an extra one, you'll end up with a value that's either 10 times larger or 10 times smaller. Miss one, it becomes 10 times smaller. Put one more, it becomes 10 times larger. And then once we have multiplied these two numbers, then we have to take a look at how many decimal digits we have, and make sure the final answer has as many decimal digits. And again, we have to count all of these zeros and account for each and every one of them. Now, if you have to do this kind of activity on a regular basis, or even from time to time, this is not a useful notation anymore. The notation is useful when we can use it in practice in a way that's efficient and meaningful. If efficiency is gone and I have to spend so much time multiplying just two numbers, then the notation has an issue with it. Keep in mind that we have different notations for different reasons. Like we have talked about the fact that we have the formal notation because it's an exact notation, it's accurate and descriptive. And so we use it in areas where we have those kinds of needs of accuracy and being descriptive. That would be theoretical discussions in sciences and also in other disciplines. Decimal notation is a much more convenient notation to use when we measure values, where we cannot be exact, we don't have to be descriptive, and therefore we switch to the use of the decimal notation, which is somewhat easier to use. And when it comes to working with decimal notation, though, we'll find that when we run into numbers like these ones, then decimal notation doesn't work very well anymore. And so we invent a new notation called scientific notation. Now, to show you what scientific notation looks like, I'm going to rewrite each of these numbers using scientific notation. And I'm going to begin by displaying this number, 602, with all these zeros following it, in scientific notation right under it. And we have 6.02 times 10 to the power of 23 entities per mole. You can see that that it already looks much nicer, more manageable, if you like. Now the 23, which is the exponent of 10, indicates that the decimal point has to move forward over 23 digits. And the reason, of course, is because the exponent of 10 tells us how many times we have to multiply by 10. So we multiply by 10, and then we multiply by 10 again, and then we multiply by 10 again until we've done so 23 times. Each time you multiply by 10, as we discussed earlier, decimal point moves forward over one digit. So if you multiply by 10 23 times, decimal point moves forward over 23 digits from where it is now, which would be there. Going forward over 23 digits. That's 1, 2, 3, 4, 5, and on until we get to 21, 22, 23. And that way, if we do move the decimal point forward over 23 digits, we sort of recover the decimal representation of the number. So the top one is now in decimal notation, and the bottom is in scientific notation. Okay, for the mass of an electron, we can write something similar. We can write it down as 9.109 times 10 to the power of negative 28. Now, I'm going to talk about negative exponents very soon in this video. But for now, you can trust me that a negative exponent of 10 actually ends up requiring that you divide by 10 over and over. And how many times? 28 times. And every time you divide by 10, decimal point moves back over one digit. And if you divide by 10 28 times, then decimal point moves back over 28 digits. From where it is now, between 9 and 1, you move back over 28 digits. That's 1, 2, 3, 4, and on until we get to 26, 27, 28. And again, by moving the decimal point back over 28 digits, we recover the decimal representation of the number. Okay, so one question comes up as to what if these zeros are not there? Because one of the advantages of scientific notation is that it sort of allows us to represent the size of a number without having to write all these zeros, whether they are on the right end or on the left end. You notice that the scientific notation representation of these numbers doesn't have all these zeros in it. In fact, the exponent of 10 sort of keeps track of them. And so the question is, what if these zeros are not present? Would scientific notation still be a good notation to use? So such as this number, 427109290, all the way to the end of it, which is 109. And if I wrote this in scientific notation, it would become 4.271092 and so on, times 10 to the power of 20. And it seems like I just made things even worse. And that's in some ways true. Now, the advantages of scientific notation are not all lost, but many of them are sort of lost when we don't have those zeros. And so the question is, so what's going on? What if we have these kinds of numbers that we have to work with? And the answer is these kinds of numbers are not the kinds of numbers that we usually see. In fact, if I see someone showing me that they're working with this number, I think my jaw would drop, because this is an extreme amount of accuracy that this person is looking at. Let me explain what I mean by that. Here I have an image on the right side And what I would like to do here is to sort of give you a gut feeling for how the sizes of place values become much smaller as you go from one to the other, moving to the right. So here I have the number 1.23, and these are three digits that are adjacent to each other. So we're talking about place values ones, tenths, and hundreds. And if you think about the size of the 1, let's say that this is what 1 is. This is how long 1 is. And then the 2 says that this distance should be divided into 10 parts, and then we take 2 parts. And that gives me, this is the size of 1 part. And because I have a 2 in the tenths, I will add 2 of those. So 1.2 brings us to this point. And then the 3 on the right side says that we need to divide one of these distances now into 10 parts and take 3 parts, and that brings me to here. You notice how quickly the size is going down. I have gone down only 2 place values, from 1 to 2 and then from 2 to 3, and already the size has gone down. The size of one piece has gone down from this much to one of these tiny ones over here. So you can imagine if I added another digit after 3, let's say 7, then one of these tiny distances would have to be divided into 10 parts, and then I take 7 parts. And the question becomes, if I have something that is this long, do I care about the 7 that comes after 3, which is so tiny that I can still see it, but it will be very, very small. And even if I keep the 7, would I need to have another digit after 7, which is now so small, it becomes like a hair. And at some point, the size becomes way too small for us to care about how many of those tiny pieces we have, and we just say none. Let's call them all zeros. And in fact, in the number 602 and all these zeros that follow, the number of entities in one mole of an entity, this is not exact. This is rounded. And a more exact value, if I remember, for example, would have a 3 here, not a 0. But the thing is, if you think about the fact that these 3 digits are side by side, and the relationship between the size of a 1 where the 6 is and the size of a 1 where the 2 is similar to what we have here. For 6, this may be a 1, and so you have 6 of those. And then for the 2, we're talking about 2 of these tiny ones. And probably beyond that, we don't care that much. Now, if you want to be way too accurate, you can show 4 digits that are not 0. Or if you want to be extra accurate, maybe 5. But by the time it gets to 6 digits, I would start asking questions. Why is it that we care about such tiny, tiny amounts when we are dealing with a large size of some kind of an entity? And in 9.109, so you notice that in this case, we have 4 digits that are not 0. That follow the zeros on the left side. And therefore here we have much more accuracy compared to here. It would be the same as the case when I was talking about putting a 7 here. So this is very, very accurate right now. And for this reason, we don't see numbers like that. This is unbelievably accurate. And so quite likely we would round this to keep the 4, 2, and the 7, and then turn everything else into zeros, or maybe keep the 1 if you want to be way too accurate. Maybe one more digit, but that's it. The rest of them would become zeros. So in the sciences, it's very common for us to have large numbers. If we do have large numbers, then it is very common for us to have the strings of zeros on either the right hand if the number is very large, or if the number is very small, to have a string of zeros on the left end. And then following those, we have only a few non-zero digits. And not necessarily non-zero, but this is where the non-zero digits begin. We don't have that many of them there. So now, another thing I would like to mention before we move on is that this is also one reason why in most science courses, you'll hear your prof ask you to round the final answer to somewhere between 3 to 5 significant digits. And 3 of them would give you this much accuracy. Now, you notice that 2 significant digits, if you show only 2 digits, like the 1 and the 2, that's not accurate enough. 1 is for sure not accurate, because with 1 significant digit, we are saying that the length is this much, whereas in reality, it's that much. We are missing on a lot. 1.2 is better. It takes us from here to here, but we are still missing an appreciable amount, especially if the 3 was 9. This would be almost another 10th. But beyond that, it becomes way too small. And you can ask for 4 significant digits, maybe 5. But then beyond that, it becomes extremely small. And so it's common for us to ask for somewhere between 3 significant digits, which would be as accurate as what you see here, to maybe 5 significant digits. Okay, the next question is, what about numbers that are not so very large or so very small? Should we use scientific notation on those? So if I have 425.7, should I write it down as 4.257 times 10 to the power of 2? And the answer is, of course not. The 425.7 is much easier to understand, less, I would say, effort in writing it down. And also, that may be the reason that 425.7 is more familiar, of course, maybe because we are much more used to using decimals compared to scientific notation. But in any case, 425.7, there is nothing wrong with it. So when the numbers are small, we normally don't use scientific notation unless there is some compelling reason to do so. Same thing with numbers that are small but not so very small, such as the number 0.175. We could write it down as 1.75 times 10 to the power of -1. But again, 0.175 works pretty well, and we continue to use it. If the number is not too small, we continue to use the decimal notation. Now, in case you do have not so very large numbers and not so very small numbers, but there are one or more of these numbers that are very large or very small with all these zeros, then if you have a mix of these, even one of these numbers, then we would prefer to use scientific notation. All right, moving back to the right, I would like to also mention that that this relative sizes that you see, this is not dependent on the actual place values of the 1, 2, and 3, which are in the ones and the tenths and the hundredths. This works for any adjacent digits, any adjacent place values. So if instead of a 1, if this distance is 100, then the 2 states that now we divide this distance into 10 parts, take 2 parts. That would be 20, and that takes us to here. And then the 3 says that we take one of these distances, divide it into 10 parts, and take 3 parts, which takes us to here. And you notice the relative sizes of these values, of these digits, is very similar to the one that we had with 1.23, which is this one. Right, so it really doesn't matter where these digits are. The relationship stays the same. I can even start with a very, very small value, such as 100th. So we would have this kind of an image. Now I have 100th. The next digit, which is a 2, says we divide this into 10 parts, take 2 parts. That brings us to here. And then the 3 says we'll take one of these and divide it into 10 parts, take 3 parts, which brings us to here. So whether it's 0.01, you can imagine this is small to begin with, and you can think of this as us looking at it under a magnifying glass, if you like. But if 0.01 was this big, then 0.012 would go to here, and 0.023 would go to here. And if the number that we have is 100, then we get 120 going to here, 123 going to here. Okay, so it's all relative sizes. It has to do with the fact that these digits are next to each other, and therefore the size relationship will be as you see it. All right, the next topic, we would like to be able to make sense of exponents of 10. And at the end of this particular topic, what we will learn is that a positive exponent of 10 implies repeated multiplication by 10. Actually, that's something you already know. So 10 to the power of 2 means times 10 times 10. If you're multiplying by 10 to the power of 2, then you get times 10 times 10. A negative exponent of 10 implies repeated division by 10, and I will have to explain how that's the case. And a zero exponent of 10 implies multiplication by 1, and I will have to explain how that works as well. Now, before I explain those, let me give you a couple of examples. So 4.5 times 10 to the power of 2, exponent is positive. We will multiply by 10, in fact twice, and therefore decimal point moves forward over 2 digits, and we get 450. If I have 4.5 times 10 to the power of 0, then it's the same as 4.5 times 1, and we get 4.5. So decimal point does not move. If we have 4.5 times 10 to the power of negative 2, then we have repeated division by 10. In fact, we divide by 10 twice. And for each of those, decimal point moves back over one digit, and we end up with 0.045. All right, so we've talked about what it is that we want to know at the end of this talk. We have looked at 3 examples, one of each, one for each. And now what I'll do is I'll talk about why is it that a negative exponent of 10 implies repeated division by 10, and why is it that a 0 exponent of 10 implies multiplication by 1. These have to do with exponent rules, and the good news is that although there are many of those, I will only use the few that we need to know, so that we can explain how is it that we have these kinds of relationships where a negative exponent of 10, for example, implies repeated division. Now I have 3 examples. The first one will provide us with a kind of a shortcut to work with exponents. The second one will explain why is it that a 0 exponent of 10 implies multiplication by 1. And then the third one will tell us how is it that a negative exponent of 10 implies repeated division by 1, by 10. Okay, so let's take a look at the first problem. Problem 1 says simplify 10 to the power of 5 divided by 10 to the power of 3. Now, when you solve a problem, of course, there are usually multiple approaches. And normally in math, the approach that is the least efficient, and usually those approaches require the least amount of thinking, we refer to those as the brute force approach. And in this case, if I wanted to use brute force, I would write out the 10 to the power of 5 and 10 to the power of 3. I would sort of write them down in expanded form. So for 10 to the power of 5, we get 10 times 10 times 10 times 10 times 10. And for 10 to the power of 3, we get 3 of them. And now we can sort of reduce or cancel out 1 10 down here with 1 10 on top. And that gives us a 1 and a 1. And then we can cancel out another pair of 10s to get 1 and 1, and then another pair of 10s to get 1 and 1. And what happens is that 3 10s on the top will cancel out with 3 10s down here, and we'll end up with 10 times 10. And we can, of course, write that down as 10 to the power of 2. Now, of course, this is fine, except that keep in mind that with scientific notation, normally the exponents of 10 are not so small. If that was the case, then we would be talking about the very not so very large numbers and not so very small numbers. Usually the exponents are much larger, such as we may have 50 on the top and 32 down here. And if that's the case, I wouldn't want to write 50 tens on the top, 32 tens down here, knowing very well that 32 tens will cancel out, 32 tens on the top will cancel out with 32 tens down in the divisor. I would, and then to try to find out how many I have left, it would be much easier to just subtract. And so a much better approach would be to write 10 to the power of 5 over 10 to the power of 3 as 10 to the power of 5 minus 3, which generates 10 to the power of 2. Now, in order to understand how the exponent works, you have to sort of train yourselves to see this when someone shows you that. So if you see 10 to the power of 5 minus 3, immediately you should see 5 tens on top, 3 tens down, and the subtraction means we are canceling. And that leaves us with 2. So the subtraction sort of tries to find out how many tens will be left after the cancellation is done. All right, problem number 2. Now this one will explain why 10 to the power of 0 is 1. We want to do 10 to the power of 5 divided by 10 to the power of 5. Now in this case, the exponents have the same size, 5 and 5. With the previous one, the top exponent was larger. Now we have the same exponents. And let's say that we're going to say, you know what, we're going to be smart about it. And now that we know of this alternative, we are going to use it here as well. And if we do that, we get 10 to the power of 5 minus 5, which is 10 to the power of 0. And then we wonder what that means, because we've never seen 10 to the power of 0. So we might say, okay, let's switch back to brute force and see what happens. Here we notice that we have 5 tens on top, 5 tens down. So all of them will cancel out. Each one will generate a 1. And when you multiply these ones and divide by the ones down, you end up with 1. So basically, now we understand what 10 to the power of 0 means. The 0 as an exponent, at least in this context, comes from somewhere. And it comes from subtraction of equal quantities in this case. And you may have 5 minus 5, like we do here. You may have 8 minus 8, 2 minus 2. But in any case, because they are the same, that means we have the same number of tens on the top and the bottom, and therefore we do get 1 because they all cancel out. So 0 basically means that after cancellation, you have no tens left. You're left with a 1. And that's why 10 to the power of 0 is 1. All right? Okay, so as you can see, my way of teaching the topic is very different from the usual approach where people would say, well, 10 to the power of 0 is 1 because by definition, x to the power of 0 is 1 unless x is equal to 0 itself, which doesn't sound like it's very difficult for someone without a lot of background in math to understand exactly what that means. But this is very descriptive. It explains where 0 comes from, and when you have subtraction of equal quantities, that means you are canceling out an equal number of tens and you end up with 1. So 10 to the power of 0 is 1. This also explains why it is that when we multiply by 10 to the power of 0, decimal point does not move. Because if I have 4.5 times 10 to the power of 0, that's the same as 4.5 times 1. And that doesn't change 4.5. And so decimal point stays where it is. Okay, the third case will teach us how to make sense of negative exponents. Now this time the exponent on the top is smaller than the exponent down. And let's say that again we're going to use the alternative approach of subtracting the exponents. And here we get 10 to the power of 3 minus 5. And that's 10 to the power of negative 2. And again, the question remains as to what does that mean now. We switch to brute force. And here we write down 10 to the power of 3 and 10 to the power of 5 in expanded form. And now we notice that what happens is that 3 tens on the top cancel out with 3 tens down. And we end up with 2 extra tens down here. So that's what this means. The negative sign means you have extra tens in the, not denominator, but divisor. The negative sign again says that you have extra tens in the divisor. And that's why it's negative, because the only way to get a negative result from a subtraction is for the second number to be larger than the first. And the second number is the number of tens in the divisor. And so you have more tens in the divisor. Basically, that's what the negative sign says. How many more? 2 of them. And so we end up with 1 over 10 to the power of 2. And this leads us to conclude that if we have 10 to the power of negative 2, then that means that we have 2 tens in the divisor. This is what we have, 1 over 10 to the power of 2. And that explains how negative exponents work, or how you make sense of them. Now, you note that this implies that you have repeated division by 10, because if 10 to the power of negative 2 indicates that we have 2 tens in the divisor, then we can write that down as 10 times 10. And if you recall, in one of the earlier videos on decimals, on multiplication and division, I believe it was, I did mention that this is a key micro skill for you to know that if you're dividing by a product, you end up dividing by each of the factors. So this is the same as 1 divide by 10 and then divide by 10 again. And you notice that an exponent of a negative exponent will lead to repeated division by 10. And that in turn implies that decimal point moves back. So if you are multiplying by 10 to the power of negative 2, decimal point moves back over 2 digits. Here's an example of that. 4.5 times 10 to the power of negative 2 is the same as 4.5 times 1 over 10 to the power of positive 2. And we can finish the multiplication and write down 4.5 over 10 to the power of 2, which is 4.5 over 10 times 10. And that's 4.5 divide by 10, divide by 10. Decimal point moves back over 2 digits, and we get 0.05. Okay, so as far as format goes, now the format of a of a number written in scientific notation, there is a very specific format that we expect, and unless the numbers have all of the features that I talk about, the number is not written in scientific notation. For a number to be in scientific notation, it will start with either positive or negative, and of course, if it's positive, you don't have to write it down. Now here comes the first thing you have to pay attention to. There is only one non-zero digit on the left side or the whole side, left side of the decimal point, which is the whole side. So this, you can only put one digit and it cannot be zero. And therefore it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. On the right side of the decimal point, you may have no decimal digits. You may have one decimal digit or two of them or three of them or more of them. You must have times 10, and the exponent must be an integer. So again, on the left side, you have a single digit which is not zero, and the exponent is an integer. Now, examples of numbers written in scientific notation: 4.2 times 10 to the power of 3. As you notice, we have one non-zero digit on the left. We have the times 10, and the exponent is an integer. 1 times 10 to the power of negative 2. We have one digit which is not zero on the left side of the decimal point. There are no decimal digits, which is fine. We do have times 10 as required, and the exponent is negative 2, which is an integer. And negative 2.8 times 10 to the power of 0, now we have the negative sign, followed by one non-zero digit on the left of the decimal point. You can have, of course, anywhere between 0 to as many decimal digits as you want. We do have times 10, and 0 is an integer. The following numbers are not written in scientific notation. 0.25 times 10 to the power of 2, we need a non-zero integer on the left. And so 0.25 is the part that doesn't work. 14.9 times 10 to the power of negative 6. Again, it's the fact that we don't have one non-zero digit on the left side. We have two non-zero digits, and two digits are not allowed. It has to be one digit, and so it's the 14.9 that doesn't work. 2/3 times 10 to the power of negative 4. We need the number in decimal format. 2.5 times 3 to the power of 2. The base is not 10. 3.29 times 10 to the power of 1.2. The exponent of 10 is not an integer. All right. Now, before I move on to the next topic, I would like to talk about why is it that we have this format. Why is it that we insist on having one non-zero digit on the left side of the decimal point? And why is it that the exponent has to be an integer? Okay, for this, we take a look at this diagram on the right side. The number that you see at the top is in decimal format. And all of these numbers that you see below it have the same size as the decimal number at the top. In fact, the decimal number at the top is the same as this one, where the exponent of 10 is 0, and therefore decimal point doesn't move. That's between 3 and 4. These are the same. Now, of course, if for some reason I want to move the decimal point back over one digit, from let's say here to here, that makes the number 10 times smaller. And if I want to keep the size of the number the same, I multiply by one more 10 to make it 10 times larger. The two will cancel each other's effects. Decimal point moves back, makes the number 10 times smaller. Exponent goes up, we multiply by one more 10, and the size of the number becomes 10 times larger, and the overall size stays the same. You can also note that if we work it in reverse and move the decimal point forward over one digit, because we multiply by 10 to the power of 1, what will happen is that decimal point moves forward and comes to between 3 and 4. All right, and of course, if I move the decimal point back over another digit, the number becomes 10 times smaller again. And the exponent of 10 goes up, so we multiply by another 10 to make it 10 times larger. So every time decimal point moves back, you have to increase the exponent by 1 to compensate for what's happening. And that way, you'll end up with the same overall size. Now, so all of these numbers refer to the same amount, and the question is, if we work on a problem, and the final answer is this number, what format do we use? Like somebody may write it down, write the final answer in this way, another person may choose to write it in this way, another person in this way. And one of the things that we don't want to have with scientific notation is lack of that kind of uniformity. And to choose a unique notation, which is, by the way, this one, we impose the requirement that there can be only one non-zero digit on the left. The requirement that there is only one digit excludes all of the ones that are below here. All of these ones down here don't qualify because we insist on having one digit on the left. And the requirement that that digit cannot be zero excludes all of these possibilities. And that way we impose uniformity on the notation. Alright, so that explains why we insist on having one non-zero digit on the left, so we have uniformity. And why is it that the exponent of 10 has to be an integer? The reason for that is because we would like to be able to interpret that exponent as the number of places where the decimal point moves over, the number of digits that the decimal point moves over. And so because the decimal point can move over 1 or 2 or 3 or 4 and a countable number of digits, we insist that it can only be 1, 2, 3, 4, and so on. It could, of course, be 0, which means decimal point doesn't move. And also the negative values, as we noticed, are allowed so that we can move the decimal point back if we want. So if I have -1, that means decimal point moves back over 1 digit. If I have -2, decimal point moves back over 2 digits. So for that reason, we're going to restrict the value of e to an integer, because if we allow any kind of a number, then we won't be able to make sense of it as we do with integers. If the exponent was something like 2.5, then I would not be able to say decimal point moves forward over 2.5 digits. That doesn't make sense, really. Okay, so exponents in math can be anything, but in this case, we don't want all the possible exponents. We just want the integer ones, so that we can talk about how many places the decimal point has to move over. All right, so that explains why we have the format that we have for scientific notation. Now, the last topic, which is an important one, by the way, because the skill that I'm going to talk about here is one that we will be using when we add, subtract numbers that are written in scientific notation. And also, often at the end of our calculations, we have to move the decimal point to write the number in scientific notation and adjust the exponent of 10. So the question is, how do we go about adjusting the exponent of 10 if we choose that we want to move the decimal point? So for example, let's say that this number is given to me, and for some reason I want to move the decimal point back over 2 digits. So that would be an example of a situation where you've done some calculations and this is what you've got. And now you want to find the answer in scientific notation. This is not scientific notation because we have 3 digits on the left side of the decimal point. So we want to bring it back to here. So decimal point has to move back over 2 digits. And the question is, if I move the decimal point back over 2 digits and I want to keep the overall size of the number the same, how do I compensate for that by changing how do I change the exponent to compensate for that? You notice that moving back over 2 digits implies the number becomes 100 times smaller, so the exponent goes up by 2 to make it 100 times larger, and the two of them cancel out. And of course, if the exponent has to move forward over 2 digits, it makes the number 100 times larger. Then the exponent comes down by 2 to compensate for that increase. The quick way to remember this is that they behave in some ways, they are the opposites of each other. If decimal point moves forward, exponent goes down. If decimal point moves back, exponent goes up. And in that way, they compensate for the changes that they are causing. So if we have, let's take a look at a couple of examples here. If we have 42.789 times 10 to the power of 4, and for some reason we would like to move the decimal point from where it is to between 8 and 9, that's moving forward over 2 digits. That makes the number 100 times larger, and the exponent goes down by 2 to make it 100 times smaller. So again, forward for the decimal point, down for the exponent. And we end up with 10 to the power of 2. Problem number 2, 42.789 times 10 to the power of 4. And now we have moved the decimal point back over 2 digits from where it is here to just behind 4, to the left of 4. And that gives us, that's a movement over 2 digits. That makes the number 100 times smaller. An exponent goes up to compensate for that, from 4 to 6. And you can also go by the quick rule, decimal point moves back, exponent goes up. And so we end up with 10 to the power of 6. This rule works, of course, this behavior is true whether your exponent of 10 is positive or negative. So in this case, again, decimal point moves forward over 2 digits to between 8 and 9. And therefore the exponent has to go down by 2. Now be careful what down by 2 means when you start with a negative number. Going down by 2 from negative 4 creates negative 6. Number 4. Now again a negative exponent to begin with, and the decimal point moves back over 2 digits. If decimal point moves back over 2 digits, exponent goes up by 2. And again, up by 2 from negative 4 will generate negative 2. Okay, so now we know how to adjust the exponent if we move the decimal point. And we have to be able to go the other way as well. If we change the exponent, how do we compensate for the change in size by moving the decimal point? The rule is the same, of course. If exponent goes up, decimal point does the opposite, moves back. If exponent goes down, decimal point does the opposite, moves forward. And here exponent went down from 4 to 2. And so decimal point moves forward over 2 digits. And we end up with 4278.9. Number 2, this time the exponent went down from 4. My apologies, it went up from 4 to 6. And so decimal point moves back over 2 digits. And we get 0.42789. Number 3. Again, the rule works if you start with a negative exponent. Here the exponent, now you have to be careful here. From negative 4 to negative 6, exponent went down by 2. Decimal point moves forward over 2 digits. And I believe the last example, here the exponent goes up by 2, from negative 4 to negative 2. And because exponent goes up, decimal point moves back over 2 digits. And we get 0.42789. Okay everyone, thank you so much for watching this video. In the next video I will talk about how we go from scientific notation to decimal notation and back from decimal notation to scientific notation. And then following that I will post videos on how we go about adding, subtracting, multiplying and dividing numbers that are written in scientific notation. Thanks as usual for watching. Take care and I'll see you at the next video.